So in the next step, we want to improve the way how the network learns. And we also want to improve and monitor the training process. And therefore, we want to go back to our code. And I added a new chapter already. So let's call it learning and training. So that's in the work folder. So that's called learning and training, and also navigated to the folder already and saved the code there. I also changed the code slightly. So I improved the appearance of our plot because we want to add one more quantity, especially the learning rate. So I say share x-axis true because it's the same x-axis, so that just looks nicer here. They also changed the base of the x-axis, so I scaled it to log10 for the same reason, so that we have a better overview about these parameters. But let us go back now to the PowerPoint and take a look at some theory. So when we ran these simulations, we saw that we can improve the way how the neural network learns by modifying at least one thing. And the main issue is the learning rate. So if it's too large, we might make lots of progress at the beginning, but then we could miss a minimum and can even lead to oscillations. And we actually saw that. And if the learning rate is too small, the learning process is too slow, and we can get stuck in a local minimum. So we want to apply two improvements. So the first one is the so-called learning rate decay, so that we start at a relatively large learning rate, or a learning rate where we figured out that it works, but then this learning rate decays over the different iterations or epochs, so it's getting smaller over time, because then we could get close to this actual minimum, and then of course we don't want to miss it, don't want to have oscillations. So we want to have a large learning rate at the beginning, but a smaller learning rate, and it decreases with the iterations / epochs. And another thing is that we want to take the shape of the gradient into account, and we want to do this by adding a so-called momentum. There are other things that we can do in principle to improve this training process. We can add so-called regularization factors that penalize the network for larger weights, because sometimes the network finds a solution by just increasing these weights to ridiculously large numbers, which is not a problem here, but later when we have other networks, for example, like a convolutional neural network, then we have to add this regularization part. We can have gradients, or we can have different learning rates for the different learning parameters, and there are many other things. So if you just Google for that, there are other ways how to do that. So we want to focus on these two possibilities to improve the training / learning process. And let's start with implementing a learning rate decay. So the idea is that you have a function. So we start with the initial learning rate. It's called alpha sub 0, and it's a function of t, of time, so of the iterations / epochs. And we just modify it in that way that we have a continuous smooth function, and we divide the current or the initial learning rate by a factor which is here in the denominator, which is essentially the product of a so-called decay rate and the number of iterations / epochs, so that the learning rate decreases constantly over time. An alternative would have been a so-called learning rate schedule, so that it does not go down continuously, but like a step function. So after a certain number of iterations, we drop the learning rate by a certain value. We want to do this smoothly like this, and therefore just apply this function. So how do we do that? So first of all, we have a new parameter for our init in the optimizer, and that's the decay rate, and we set a default value to 0. And of course, we have to remember the decay rate, and now we have a current learning rate, which is the learning rate that is a function of time then. And the initial value of the current learning rate, of course, is the initial learning rate. And we also have to count the number of iterations because we want to multiply this with the decay factor and divide this divide the learning rate by the product of the current number of iterations and the decay rate in order to get the current learning rate. So we just go to our update parameters, and instead of having the learning rate, we use the keyword, or we use the variable current learning rate. Then we need another method. We just call post update parameters, where we just count the number of iterations, because we have to divide the learning rate by this product number of iterations and the decay rate in order to get the current learning rate. And then, of course, we have to modify the learning rate itself. And we will do this in a new method that we call pre-update params. So if we have self-decay, then we just calculate the current learning rate by taking the initial learning rate and divide it by this product self-iterations times self-decay, which is essentially this equation. So we can just go back now to our code. And just add this. So we go to my ANN, go to the optimizer, and then just add the decay. And we add the decay. Also here, want to keep that in line. Then we want to have the current learning rate. So we want to have the current learning rate, which is in the first step before we modify the initial learning rate. Also here, want to just keep everything in line. And then we also want to count the iterations. And we start at 0, of course. Okay, so we have this part where we update the parameters, and now we want to do this with the current learning rate. So if we don't change our learning rate, the initial learning rate will be the current learning rate. So if we don't have a decay, we still have our constant learning rate. So it won't change. It's just a different name, so the different name of this variable, which has the same value. So nothing would change. That would work. And then we have to count the iterations. So we do this with post upgrade or update, sorry, update params. To post update params. And we just add 1 to the iterations. So we just count the iterations. So this is just itself iterations plus 1. That's it. Then we need another method, which we call pre-update params. Which just performs the calculation. So if self-decay, so if that's true, then we calculate the current learning rate by saying, okay, we have the initial learning rate, and then we multiply this. I want to add a line break here. We multiply this with this factor, which is 1 divided by 1 plus, and then we have the product of the iterations, so self iterations times the self-decay. All right, so that's pretty much it. So we have the decay, then we have the initial learning rate and the current learning rate, which is the same if we don't have self-decay. But if we have self-decay, then we calculate the current learning rate by this equation that we derived. So we have the learning rate and divided essentially by the number of iterations times the decay. And then we, of course, have to count the number of iterations. So we can then just compile our network. And then if we call our optimizer, we can set a certain decay rate, let's say 0.02. And of course, we want to monitor the change of the learning rate over time. So we want to add one more column, and we also want to plot this. So we also want to then have 3 subplots. And then we also want to just add one more plot. So don't make this anymore. And of course, that's number 2. And this is the learning rate. And let's include a variable name alpha by using LaTeX code. And let's make sure it's a raw string so that it all works. So we just plot the learning rate over time. And of course, we also want to monitor the learning rate over time. So that's then number 2 here. And let me just import our network and also import the optimizer. And the optimizer now, if we just go to the optimizer, it now has our learning rate. And of course, it's 0.1 because that's the default value. So it just has the learning rate here. And then we also want to take a look at we want to monitor the current learning rate. Just the same because we just initialize the optimize. So we just copy and paste it and just go back to our main function. Yeah, and then we have our learning rate here. We're almost done. So of course we have to change the learning rate. We have to calculate the current learning rate, and then we also have to count iterations. So what we do now is that we just call the optimizer and first call pre-update parameters. And we have to do this, or we want to do this before we change the weights. And then we also want to run the post update parameters where we just increase the iterations by 1. So that kind of should work. Let me just rerun it. So we actually don't need all the plots here anymore. Let me just rerun it. And of course you can rerun it too. And then let's see whether we get the correct plot. see that we don't get a value that's a lot better than before, but we haven't looked for the optimal arrangement of these parameters. So we have those plots here. The learning rate decays. The accuracy goes up, not perfectly, but as I said, we haven't found the optimal set of parameters because we want to add one more thing, and that's the momentum. So therefore, let's go back to our PowerPoint slides. So I just want to summarize what we added to our code. So we have our optimizer. We added the learning rate decay. We just added this to our optimizer. We went back to our code, added one more column in the monitor. We essentially left the code as it was, but we just added the current learning rate to our monitor. Then we also added the pre-update parameters for calculating the current learning rate and also for the post-upgrade parameters for counting the iterations which we need for calculating the current learning rate. Then we just created a plot, and you should see something like that for a different set of parameters. So we're not done yet. So we now have to add the momentum, and the momentum is something like rolling average over the gradient. And I want to explain this problem first. So the normal gradient descent is just this equation. And if we have our loss function on the right-hand side, like here, and if we have a global minimum that we want to reach, it could be there's a local minimum in between. And if we have a large learning rate, we can actually very likely skip the local minimum, but then oscillate in the global minimum because the step size is too large, so the learning rate is too large. Then we said, okay, we have a learning rate decay, so at the end we will have a smaller learning rate. But then the problem is, if we have small steps, we can just end up in the local minimum. So I want to illustrate this here. So we can just, in principle, get stuck here, and then it's gone. And we never will reach the actual global minimum. However, what makes sense then, instead of getting trapped in this local minimum, we can calculate something like the average of the gradient here. But we don't want to calculate the average of the entire gradient throughout the iterations, because then we would just get a function that looks like this and wouldn't help. So we only want to calculate the gradient, the average of the gradient of the current iteration and maybe a few previous iterations, so that we get the gradient of this. And we want to do this throughout the process. So not for all iterations, for only, let's say, the previous iterations. So therefore, we want the algorithm to forget the gradient of iterations which are long ago, because they do not contribute to the current shape of the loss function here. So we kind of want to forget the previous iterations. So, and that's the reason why it's called a rolling average, because we only calculate the average for the current iteration and a few previous iterations. So in principle, if we just go back to the definition of an average, we will have an equation that looks like this. So we have the gradient of our loss function with respect to a certain parameter raw at iteration I. And if we just want to do this for the previous n iterations, let's say 10, then we just sum up the gradient, the values from the previous iterations, and divide it by n. However, we want to do this in a more clever way, because we want to weight these the contributions of the average differently. So it makes more sense, for example, that if we calculate the average, that the gradient from the current iteration has a stronger contribution to the overall average than the gradients from previous iterations, especially if they're long ago. So the further the previous iterations away, the less we want to have it have a contribution to the overall average. So for the current iteration, we want to have a large contribution to the current average to the average, and for iterations which are further away, we want to somehow weigh this that the more distance the iterations are, the less they influence this average. So it will be the rolling average, but again with different weights. It fully makes sense because the further away we are from a location there, the less it makes sense to take it into account for calculating the local average. So one possibility is then to multiply this with a weight. Let's call it mu sub k, because we want it to depend on the distance from the current to the current iteration. So if it's k iterations away, then it should have a smaller weight compared to the weight from the current iteration. So how can you do that? A simple way is to, for example, pick up or just to set a mu k that has a value between 0 and 1. So we have this mu, let's call it mu sub 0, which has a value between 0 and 1. And I want to illustrate how we could actually do that. So let's start with our first iteration. Then we can't calculate an actual average, so we just have the gradient. In the next step, we have iteration number 1. Then we want the current gradient to contribute more to the average than the previous value an iteration ago. So we multiply this with this momentum mu sub 0, which is between 0 and 1. So let's say 0.5, 0.9, 0.8. Then in the next step, so we have 3 iterations. Then iteration 0 is even longer ago. So we multiply this again with mu 0. So the factor is even smaller because mu 0 is between 0 and 1. And the previous iteration, so the gradient from the previous iteration, is also multiplied with mu 0, but only once because just 1 iteration ago. The other iteration is 2 iterations ago, so we have the factor mu 0 squared. So therefore, again, the gradient from the current iteration has the largest contribution. The gradient from the iteration before has a smaller one, and the gradient from the iteration 2 iterations ago has an even smaller one. And we can just continue that. So every time we move away from a particular value, it gets less and less important, and the weights are getting smaller and smaller, so that the contribution to the overall average gets smaller and smaller. So the current gradients, so for the values close to the actual location now, have a higher contribution, a larger contribution to the overall average. So that is the idea. And now we just need to implement this in our gradient descent method. So if we just do that this way, for mu k, it has just the value mu 0, so the initial momentum, to the power of k. And eventually it will not play any role at all. It's, imagine we have, I don't know, like 10,000 epochs or so, then we have this prefactor mu to the power of 10,000, so that the early iterations do not play any role anymore. So now we just need to implement this in our code. And you saw we can do this recursively, and that's how we implement this in our code. So we have to add this to our standard gradient descent algorithm. So that's the gradient descent algorithm again. And now we just add this momentum mu. And for the iteration I plus 1, we multiply the old mu with the previous one. And the new mu is then just the previous mu minus gradient descent. And for the next step, so for I plus 2, we take this part here and multiply this again with mu. Then we have exactly what we discussed earlier, right? Every time we multiply this factor here, so the gradient times alpha with the mu, And in the next step, we do this again. So the further away this is, the less it contributes to the overall average. This is exactly what we discussed. So, and if we just include this recursion in our optimizer, it just calculates the rolling average automatically. So what we have to do now is that we go to our optimizer, then we also add the momentum. Let's start with 0 as a default value. We also need to remember that. And then if we go to update parameters, we have to distinguish two cases. So if we have a momentum, we have to remember this momentum because we always multiply this momentum with the current equation that we just discussed. So like the old momentum times the height from the gradient descent. And in order to save this, we want to add a new attribute in the layers. And we want to call this weight underscore momentums for the weight and bias underscore momentums for the bias. And in the first iteration, it will not have these attributes. So we just look into the layer, look for a string where it has these attributes. And if it doesn't have these attributes, we add them. And we add a matrix with 0 like, and we know what the shape of the matrix is supposed to be because we know the dimensions of the weights and the biases. So we just go into the layer, look at the attributes, weights, and biases, and then we can add these matrices. By the way, it doesn't matter if we look for the string weight momentums or bias momentums because we have to add both anyways. But of course, it has to be the exact string. So then we just apply our equation here. So we just take the self-momentum, multiply this with the weight momentums, whatever it is, and then add the normal gradient descent part. And that gives me a new variable we will call weight updates. And these new updates will be the new weight momentums because in the next step, we will multiply this again with the momentum. So that's the recursion we just discussed earlier. Here's the factor mu, and we constantly multiply this with the factor mu. So the sum here grows over time, but the further away it is from the current iteration, the higher the power of the momentum is. And we want to do this for the biases as well. And then, of course, if this is not the case, we just do, as before, the normal gradient descent. So therefore, let's go back to our initial code, and let's implement those modifications in our optimizer. So we just expand this a bit that we have more space here. And then we go to the optimizer, and then we include the momentum. With the default value 0. And then we also want to save it. And now we have to apply these modifications. So we first of all go back to, or go down to the update parameters. And now there are two cases. So if self momentum then we first have to check whether there is already this attribute. So you say if not has attribute, and we just feed in a layer. So the dense layer, dense 1 and dense 2, and we look for the keyword weight momentums. So if that's not the case, then we add this attribute. So we just take the layer and add weight momentums. So we can actually copy and paste that. Equals NP zeros like, and then we know the size of the matrix or the shape of the matrix by just looking into the weights. So again, zero like just takes any numbers that are in the current memory instead of specifically assigning zeros like NP zeros, which is a bit faster. It will not matter a lot in the code because you only have to do this once actually, because then the attribute has been added and we don't need to do that again. So we do this for the weights and we also for the biases. And because the attribute weight momentum does not exist and also does not exist for the biases, and that's the reason why we can do that here as well. All right. So then, maybe I leave some space here. So then, if that is true, so if we have these attributes, then we can now update our weights and the biases. So we just call it weight updates. And then we just apply our recursion. So we just say self momentum times layer weight momentums minus, and then there's the normal gradient descent part now. So that's then self current learning rate times layer d weights. So when we construct our or build our convolution neural network, we will also have our dense layers, but we also will have different convolution layers. And then we can use the same optimizer if the keywords in the layers are the same. So if we also call the weights and the biases really weights and biases in our convolution layer, and then we can also update them accordingly. So that's the reason why we do this in a more generic way, so that we can use the optimizer for the other neural networks that we want to build at some point. Okay, so we have the weight updates, self momentum times self weight momentums minus the current learning rate times the weights. And then, of course, we reset the layer weight momentums, which is then the weight updates. And we do the exact same thing for the biases. See. So we just call it bias update. It's bias momentums. Then this is the biases. So make sure that you don't confuse the different learnables. And then we just rename weight momentums in weight updates with bias. All right. So that's the case then if we have a momentum and then we have these updates. If that's not true, so else, then we calculate the weight updates as before. So, so sorry, so we just calculate these before. So that's the weight updates by just changing the weights according to the normal gradient descent. So we'd say learning rate times layer d weights, and we also do this with the bias update. Be careful that you take the minus if you just perform copy and paste. So, and then we have these two cases. So either we have the momentum, then our updates are like this, and they're updated recursively with the momentum because we always multiply the momentum. And then we just buy the, so the normal gradient descent part. And if that's not true, so if we don't have a momentum, then the updates are just the gradient descent. So we now just go to the next line and just say, well, these are the updates then for the biases and the weights. If we don't have momentum, because that's what it says, else. So that is the implementation of the momentum. So we can run our function again. And then we can go back to our optimizer and we can also add the momentum. And I want to add some specific numbers. So let me just add the learning rate again. Let's say we start at 0.1. Then let's say we have a decay, 0.01. And then we also want to add a momentum. And let's say 0.8 or something. So we call our ANN again, and then we run our code. There's a typo. So let's check the typo. So let's fix it together. So that's actually what happens most of the time. So let's see where the typo is. So the typo was just here. So I, from copy and paste, had accidentally the plus here. I want to show you the typo again. So if we go back and run the network, it says the local variable it's reference to the local variable before it's been assigned, and the reason is plus equals, because that means weight updates equals weight updates plus something, and that's of course first of all something we don't want to have, and of course it would be wrong. So that was the typo. I kept it here because that's something that can actually happen. And it's actually kind of misleading because you might think, okay, let's just calculate it here, but it was just a plus. So that's the reason why I left it here, and now we can rerun it. And then let's see how our code performs and whether we have a better result. So code runs and it goes up to 0.5 something. And here we go. It's not ideal, so we can play a bit of the parameters, and I did. And the best value I obtained, which was 93.8% when I have a learning rate of 0.2 and a decay of 0.01 and a momentum of 0.9. So that actually means that the geometry of the loss function is pretty bumpy. So there are lots of local minima. And that's the reason why the network did not really perform extremely well. And therefore, it makes more sense to take more of the momentum. So that's one thing. So that's the best value so far I got after trying it a bit. And I want to encourage you to play a bit with this hyperparameters, and maybe you get a better result, and just let me know and write in the comments. Okay, so now we want to rearrange the code a bit because we want to now apply our network to the data. And so first of all, we need to train the network. So that's what we did many times now. And we want to put this into a function so that we don't have to run the whole code all the time explicitly. So it makes more sense to put it into a function. That's the first thing we want to do. And the second thing is then after we have optimized our training, we want to save the weights and the biases because, as remember, that's the memory of the network. And then we want to apply this to a new data set. And we want to see how it assigns the classes of the new data set depending on how much how many data or how much data we included for the training process and what are the training parameters. Because at the end, you want to train a neural network, and then of course you want to apply it to new data, and that's what we're going to do in the second half now.